even with microreactors. And so what we did is we bought a microreactor. They unfortunately have a macro price. And we tested them with the chemistry that we are very familiar with. So we tested them, for example, for the photodecarboxylation. We just published something in Organic Letters. And here's our setup, less sophisticated, but very conventional. Microreactor here under a UV panel. The UV panel is way too large. I tell you that already. Syringe pump to get in. And because we have a cooling channel as well, there is another pump here for the cooling water. All right, the thing here is a commercially available reactor, not developed for photochemical reactions, but it's made out of glass, so you can use it as such. Dimensions, everything is given there. And the first thing we did is, well, let's have a look at the light penetration, so this Beer-Lambert law thing. We work in acetone water. So acetone is our co-solvent, but acetone also is actually where the light goes. So here we have a sensitized reaction, and the sensitizer is there in huge quantities, 50 volume %. And this is the UV spectrum of acetone. The gray dotted line here, spectrum, is the emission of the lamp. And the vertical line here is the cutoff wavelengths of the glass we're using, and the glass here has a protective function, so we're using Pyrex instead of quartz. Now when you now determine the extension coefficient of acetone there, where your cutoff is, and you put that into the Beer-Lambert's law, for the microreactor, this is the profile you're getting. And the microreactor has a cutoff here at 0.5 millimeter. So even at this very high concentration of acetone, you still have complete penetration of light through your microchannel. The molecules on the other side of the reactor still get a chance to pick up some light and to react. When you do the same thing for the Schlenk flask that we put into the Ryonet reactor, the Schlenk flask has a cold finger inside. So you put a cold finger into a tube, and that means your diameter that you're working with, because you're irradiating from all sides, is 32, what is it? It's some few millimeters. It's 4 millimeters. And when you now look at the Beer-Lambert's law, 4 millimeters is nothing, not even my fingernail here, my little pinky. But 4 millimeters is already quite a huge distance for light to travel in a solution of acetone at this concentration. So it means up to 1.5 millimeters you have penetration of light, and then is complete darkness. Most of the solution is in complete darkness. It doesn't matter in batch systems, we don't care so much. But when you plot it here, you really get this very frightening result. And then we just did a range of reactions. I'll only show you one. Don't want to bore you too much. So the cyclizations again, where X was either CH2 or sulfur. And the first thing we did is we tested radiation times. So with a flow rate, you can control now the irradiation time or the residence time. And we checked then for the Drell device and for the batch system the yield. You can isolate the yield. You can isolate the product very easily. And after 1 hour of irradiation or residence time, the Drell device gave a yield of 77% for the CH2 case and 80% for the sulfur case. The Ryonet reactor gave 69 and 72. Now these numbers are very similar, but we are comparing two different things. The Ryonet reactor has an advantage. It has 16 lamps. The Drell device has only 5. So in order to have fair play, we took 11 lamps out of the Ryonet, and we repeated the experiments with only 5 lamps in the batch system. And now, of course, you can make a fair comparison. So with 5 lamps only, now the carbon case gave 19% yield, the sulfur case 21%. So in terms of yield, the Drell device was 8 or 58% more effective for the carbon case, and 8 or 59% more effective for the sulfur case. But that's only half of the story, because basically you have very different systems here. So this is just a list of some of the parameters of the reactors. And the most important one is probably this ratio here, which is known as the surface to volume ratio. We call it the irradiated area to volume ratio. So we only now focus on of the microreactor, how much of its overall area actually is irradiated. The other part is only the frame and other things. And you can see that the Drell device has a much higher value here. The other thing we wanted to know is, well, we have all this light. So what is actually the lamp power per irradiated area? So it tells us also how efficiently the whole system is designed. And you can see here that the values are comparable, but the Drell device has, for the fully equipped Ryonet reactor, almost the same value, but with the 5 lamps we have much more power of light per area of actually microchannel. So that is one reason. Light penetration is one reason why the reaction is better. The other reason is why we have a better reactor geometry and a light coverage. We then also looked at the energy efficiency. That's something we picked up here from Professor Liu's group, who had published a simple equation. So we did the calculation, but we also did on edit the area again, because in our cases the light sources is larger than actually our reactors. So we thought we have to take that into account. And if we do that, and here are the numbers again, the Drell reactor again also shows a better energy efficiency. It's not the quantum yield, it's energy efficiency. So how efficient do the reactors use the light? And the higher the values, the better it is. And the last thing I calculated just before this lecture is the space-time yield. It's an expression that caused us a lot of hassle because it's a very simple equation, and you always read that microreactors have a better space-time yield. So we calculated that, and we actually miscalculated it a number of times, because here's an amount of, not fluorone, it should be phthalimide, excuse me, converted in the microreactor volume, not the total volume you're pumping through. It's the volume you have in the microchannel, divided by the volume of the reactor and the irradiation or residence time. And if you do that for these 2 reactions with the 3 setups, the space-time yield is indeed, as you would maybe expect, highest for the Drell device. So all these calculations point to the same thing. The Drell device is better than the Ryonet or the batch system. In particular, if you do fair play and you compare the same amount of lamps per reactor. So this rather than that one.